Yeah. So again, just to recap what I've said so far, um, in the work on a compositional model of graphs, which I called toggle, uh, so the theory of graph language, or a language for the theory of graphs. Um, One of the things that I mentioned was that it is possible to build out a framework to investigate infinity categories. And part of the motivation for that from a mathematical perspective is that there are about 6 or 7 different definitions of infinity categories. Um, uh, there's no compelling reason to choose one over the other, and there's no real framework to understand the design trade-offs between the two. Now, there is this space that's been opened up recently in Cosmoi, um, where people are rather than picking out any one definition, they work in a broader universe of infinity categories. But at that point, you're so far off the ground that it's a well, it's certainly an interesting level of abstraction. Let's put it that way. Dizzying heights of abstraction. Um, but the trick that I employ has to do with being very, very conscientious about your dependencies, and then systematically closing those up in terms of the syntactic elements that you've got lying around. So if you think about it from the point of the process calculi, there are 2 dependencies in the pi calculus, right? One is you need to say what the base gadget is, so the zero process, and the other is the set of channels, right? And you can provide the set of channels via this recursive loop in terms of what you've got available for processes. So you've closed up one of the 2 holes. Now it turns out that you can also do other tricks, right? So you can have you can close up that hole for the zero process by having red processes and black processes, right? And so the black zero is actually any red process, and the red zero is actually any black process, right? So you can, and of course you don't have to do it for just 2. You can do it for n, where n is the number of colors you've got. And so in that way, you can also close up the hole that way. So the people understand what I'm saying. So you have some syntactic construction. The syntactic construction is has got some holes in it, so where you have to provide some information in order to use the gadget, and you systematically close up the holes using some kind of reflective or recursive trick. Does that make sense? People following along with the general principle.
Yes, I'm following.
Cool. All right. And but because you have all this recursive or reflective machinery lying around, you can do all kinds of crazy stuff. So for example, with the red and black processes approach, one of the things that you can do is to you can treat it as a time sharing system. So when you hit a zero, that means you're suspending all activity. So like when you're running a black process, then you run down to 0. When you hit the 0, you toggle over to the red process, right? So it's a kind of time sharing system. So it says, okay, I'm gonna so you could think of the colors as the actual physical, the physical resources that you've got. So coloring means mapping onto the actual cores that you've got. So then you run down to black 0. Well, that toggles you over to red. So then that red process runs until red 0, and that toggles you over to black, and so on and so forth. So we get a kind of time sharing mechanism, and in fact a syntactic device whereby programmers can say, run this on this resource, run this on that resource, and where to do the cutovers. So all of that becomes available syntactically, and it's for free. It's just because we use this recursive, dependency closing kind of mechanism. Does that make sense? Are people following along?
Yeah, that's pretty clever.
So with respect to categories, with respect to, so we can think of graphs as more lax than categories, right? So graphs have vertices and edges, but you're not guaranteed that all compositions are closed, if that makes sense, right? So the thing that you don't necessarily have. So in a category, if you have a morphism that runs from X to Y and a morphism that runs from Y to Z, then you're guaranteed a morphism. In other words, let's say that the first morphism is M1 and the second one is M2, then you're guaranteed that the morphism M1 compose M2 is a morphism that runs from X to Z. Right, so you automatically have that edge in the graph, right? You don't have to go through the dog leg. You have an edge, which is the composition of the two that runs from one to the other, from X to Z. So in a graph, you don't necessarily have a composition. That's one way to think about it. Now, if you treat it as paths, then you do have composition. But if you treat it differently, then if you treat it more atomically, then graphs can be thought of as more lax. Also, categories always have self loops and graphs don't, right? So if I have a vertex X, which is an object in a category, then I have an edge that runs from X to X, which is the identity. There may be others, but I at least have that self loop. But graphs don't necessarily have those self loops. So we can think of graphs as kind of more relaxed than categories. So, but what we can say is that a graph as a type constructor has got to have two inputs, right? There are two dependencies. You've got your vertices and you've got your edges. And so because your term constructor has a your graph constructor, your graph type constructor has these two dependencies, then we can play the same tricks. We can close up those dependencies and then insist upon an algebra that takes advantage of the interior structure of what we're supplying in those the recursively closed dependencies. And that's really all that's going on with toggle. So the thing with categories is that you're essentially just adding additional equations, right? So you're adding these additional constraints, right? So you're saying that you have to have these self loops, and and with respect to composition, one of these self loops, one of these kinds of self loops has to be invariant with respect to composition. So it's an identity with respect to composition. And so you can think of this. One way to think about this is that you freely generate all the closed up syntax, and then you impose these additional behavioral characteristics as equations on top of the freely generated syntax. So one way to think about it is we're just, when we recursively close the loop, we're providing a bunch of additional tagging structure on the syntax. And then using the tags, we can impose certain kinds of equational constraints on the freely generated syntactic structure. So that's the same trick that we employ whether we're doing the row calculus or the red-black sets or red-black processes or any kind of any one of these things. It's the same recipe. Find your dependencies, close them up reflectively, and then impose the equations on the syntactic structures that you've generated in order to build a syntactic model of the gadget that you're interested in. So the thing about infinity categories that's interesting is that well, first of all, the idea of these higher categories is that you don't just have objects and morphisms. In general, we call them cells. So objects are 0 cells, morphisms are 1 cells, right? So if a morphism runs is an entity that runs from a 0 cell to a 0 cell, then a 2 cell will run from a 1 cell to a 1 cell. And then a 3 cell will run from a 2 cell to a 2 cell, and so on and so forth, right? So that's the, so if you're doing 2 categories, then you have not only morphisms between objects, but you have this other kind of thing between morphisms. And then when you have a 3 category, and you have this 3 cells, which are running between the 2 cells. So you might think about this in terms of higher dimensional shapes, right? So if you think about the 1 cells as kind of lines between dots, then you can have faces that run between lines, right? So if you think about objects as vertices, then 1 cells are edges, 2 cells are faces, 3 cells are volumes. Is that making sense?
Yeah, well, I'm getting the general idea. Yeah.
Okay. Just trying to give some intuitions and some motivations for what's going on. Mm-hmm. And so, and since you can kind of imagine this happening in ad infinitum, then the obviously the one thing you might ask yourself is, well, what's happening at the limit? So the infinity category is to investigate when you take that process out to the limit, what kind of thing happens. And the interesting issue is that if you follow geometric intuitions, you end up with slightly different objects than if you follow more syntactic intuitions. And so this is what gives rise to the different infinity category definitions. So that's something that that is, you know, one way to understand, why is it that at infinity our intuitions are beginning to break down, right? And really, it's because we're following different approaches to our understanding of the generating process. So with the reflective approach, you can again do something that's interesting, right? So you take a a term constructor, but now your term constructor has an infinite number of holes in it, and so you have to you have to tag each of those different holes. And that leads to a whole bunch of interesting dynamics. In particular, it means that you're now having to import a tagging structure that is how do I say this? Philosophically, I am at odds with any kind of infinitary object. I want to write down infinitary objects as finitary objects. Does that make sense? So rather than me having to take on or together as a communication device, us having to carry the burden of having faith in some explicitly infinite gadget. I want to be able to communicate something that is finitary in its nature, but that will generate this infinitary behavior. So, like to bring this down to a little bit more concrete, right? So if I'm going to try to communicate to you the natural numbers, if I say, well, it's got 1 in it, and it's got 2 in it, and it's got 3 in it, right? If I have to make all of those statements before I have successfully communicated to you the set that is the set of natural numbers, I have a problem, right? Because for beings that only have finite time available to them, talking about those kinds of sets or communicating those kinds of sets will take too long, right? It'll take longer than the time we have allotted for any one communication event. So instead of communicating the natural numbers in that way, I communicate a program or a rule that will generate the natural numbers. So I can give you the data of the program in finite time, right? So whether you write it down in terms of the Haskell program or any other kind of program that lazily generates the natural numbers, you know that I can communicate the information contained in that program in finite time. And so, as soon as you get to infinity categories, and you have some, a gadget like an infinity category, then you run up against this kind of philosophical consideration, right? So the philosophical consideration is, to communicate an infinity category in finite time, what apparatus do I have to have lying around in order to do that? And that runs up against another philosophical principle. So if I have to have an apparatus that's already computationally complete, then that means that my communication is now dependent upon so again, this is about being careful about your dependencies, is now dependent upon that computational apparatus, right? So that was one of my critiques against the pi calculus, right? The pi calculus needed an infinite supply of names, and the names had to have an effective notion of equality, right? So those two things taken together provide an insurmountable obstacle if you can't look inside the structure of names. As soon as names have some kind of structure, then you're back into this place where you can communicate the name set, because there's a program that provides the information, and you can use information about that program to determine a notion of effective equality on names. So it's the same thing. It's the same thing here with infinity categories, right? So ignoring for a moment that we have an infinite number of holes, we have to tag each one of the arguments to those holes with some kind of tag, and that tag needs to be communicable in finite time, right? So I need to be able to talk about the total space of tags available to me in finite time. And if that means that I have to import a notion of computation in order to specify infinity categories, then that's effectively another hole or another dependency in infinity categories. So what you want to do is to find either just flat out say, okay, infinity categories are going to require this much of a notion of computation in order to specify, or we're going to be able to reuse some syntax or some piece of the infinity categories in order to build those tags. So that's a lot of information. So any question or comments about that? People following along?
Yeah, I'm following along. Now I'm interested in finding out how you construct these tags. Or
Yeah,
is
yeah,
that's okay?
yeah, exactly. So the nice thing is that you can there is enough generating structure to build out the tags, but you have to be careful. So if you look at the toggle language, you'll discover that there's enough generating structure to build out the tags, but there's sort of this extra level of recursion that goes along. So I'll just sketch out briefly a little bit of what I'm saying. So again, with toggle, what we were saying was you have two holes, say x0 and x1, and depending on how you fill those holes, that's your that will generate that's enough structure along with the other operations on the type to generate your graphs. Now the interesting thing is that and so obviously you can extend this to 3 holes or 4 holes, but now let's say that we have x0, so that's going to be the hole for the objects, and x1 is going to be the hole for the morphisms, and x2 will be the hole for the 2 cells or the 2 morphisms, right? So in general, xn is going to be the n cells, and it goes on, right? So that the first problem that you have is that you have an infinite number of holes. So you're addressing the holes is going to require ultimately some means of some kind of computational structure in order to communicate the just the list of holes. The other thing that's of interest here is that when you fill them, when you fill the holes, you're going to want to provide some kind of tagging mechanism. So let's take a look at this. So the general shape of this is, for some constructor C, which has some number of holes, I can eliminate all the holes, right? So this is an operator not on, it's not defined point-wise, right? It closes up all the holes. So whatever C is, I can build this recursive structure. So it's one level up. So R acts on operators. C's act on, sets or whatever the elements of your category are. R operates on C's, right? So it's one level up from that. And so, one example of a kind of closure mechanism would look something like this. Now, this is not the final product, but it will look something like this. Now, I could just put RC here. Right? And oh, gosh darn it. So that's one way to look at it. And then I have to be careful about position, right? So I have to know that these things came. So something that can you guys see my mouse?
Yes.
Yes.
So I have to know that these things came in on this position because they're exactly the same as these, right? So so I have to be super careful about the positions, and that kind of positional tracking can be a little bit tricky, right? So another approach is to tag them, right? So I put a little tag, so following Rolang, right? So I have at sub-0. So this is like making a name out of something. And then the next one would be at sub-1. And in general, we have at sub-n. And notice now that our tagging mechanism is effectively the natural numbers. And so if I want this thing to be communicable in finite time, I have to, whenever I'm communicating R sub C, then I also have to have communicated as a part of our background assumptions a program for generating the natural numbers. And if we want infinity categories to be a foundational gadget, right, one in which we realize computations, then we would want to have these things come out of this structure. Now you can see that in fact in this first gadget here, I do have enough structure, right? Because what I'll get is stacked C's, right? So if I don't take this branch here, then I'll get a C, and then I either ground out with a star, one is the one element set, which is, we typically denote that element as star, or I go down the other branch, so I'll get another C. So I'll either get C or so I'll either get star, C star, CC star, CCC star, etc. Right? So each one of these, each time I iterate through, I'm getting N Cs, and so I can use this structure to give me the tagging mechanism. Is that making sense?
Yep.
Okay. All right, cool. So then the next trick, once you have that, the next trick is you might not want to consider, or how do I say this? You can consider different variations by only taking power sets of these things. So instead of taking the whole thing, you take power sets of these things. So that will give you that will give you the ability to take substructures that are still infinity categories, or have a kind of they share the structure of the free one, but are substructures of those things. So that's another refinement that we can do. And then once we do that, we can also start playing some new games. So notice that this thing is the same as if I were to tack on one at the beginning. Right, so I can define an operation like this. Right, which so I can go either to the left or to the right. It's easier syntactically to imagine it like this. And notice that this gadget here is isomorphic to this one, right? I just do to map the slots, to put the slots in one-to-one correspondence, right? So think of each of these things as slots. I have an infinite number of slots here. I have an infinite number of slots here. To put them in one-to-one correspondence, I just subtract one from the tag, right? So this will go into that slot. The next one will go into that slot, and so on. And so I can set up a one-to-one correspondence, right? So I have an interesting set of dynamical operators. And in fact, the operators from dynamical systems now all apply to this kind of syntactic structure, which I've used as the basis for building my infinity category. Does that make sense? You're following along with what I'm doing?
Yeah, that piece of it I understand. I'm following there.
Oh, so what you said that piece? Was there
Yeah,
something?
I was getting confused earlier with the mechanism in the with the zero and the sub-zero and all that. I had to kind of think through that, but I guess
Here,
I know where I'm wanting to get to as far as how do you define express something infinite in finite terms. So I'm
sure.
getting there.
So think about it like this, right? I've got this plus, you can think of this as like an automata. It corresponds to a finite state machine. Okay, and one is just the star. It's the one element set with a star in it.
Mm-hmm.
Okay, so hang on, let me get my connections. All right, so come on. There's that. Okay, there we go. And then duplicate that. All right. So if I go down, if I come in and I go down this path, then let me just label this with a star. Is that? Yeah. Okay. And then. Hopefully that's visible.
Mm-hmm. Yeah.
Okay. And then over here, we're going to put C around whatever it is we generate. Okay. So I'll just put a dot, dot, dot. Come on. All right. So I probably need to make all of these bigger. Come on. There we go. Okay. All right. So, and then move this over. Okay. Slightly better. All right. So, and then I need one more arrow, which is a loop out.
So just to understand what I'm looking at here, so you're creating a set, and if I'm going down the left side, the star indicates just one element. If I go down the right side, is it still one element, or it looks like there's going to be multiple elements going down the right side?
Well, think about it like this. I'm literally just generating a term. So this is generating a term.
Oh, okay.
So if this is my start position,
Mm-hmm.
I come out of here and I generate the star and I stop. That's this branch.
Okay.
Okay. And this one, if I go down this branch, I wrap C around whatever is the rest of it. And to get the rest of it, I go around the loop.
Okay.
Okay. So now if I do a star, then I'll just have C star. If I do, if I go down this branch, I wrap C around whatever is the rest of it. Okay.
Mm-hmm.
So remember, I've got this awaiting C, and now I'm going to wrap C around whatever is the rest of that. So so if I just do it once, so I go down this, wrap C around whatever's the rest of it, then I go C star. If I do go down this branch, I'll go C, C, and then what's waiting? Well, if I go down this branch, it'll be C star, C, C star. Otherwise, I'll go C, 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 whatever's the rest of it. If I go down this branch, it'll be C, C, C star. Otherwise, and around we go. Do you see?
Yeah. Okay. I'm following there.
So that's one way to interpret the type equations like this.
Mm-hmm.
So type equations correspond to automata in many circumstances. So essentially what I'm doing is I'm kind of giving a language theoretic characterization. Now this is more complicated, right? Because I don't just have one hole, right? I've got multiple holes. I've got infinite holes. So in some sense, I've got infinite branching, right? So I've got C, but what's going to go in here is an infinite list. Some of them will be stars, some will be C's wrapped around something. Does that make sense?
Yeah,
So the first level of this will be this set that, you know, it's like C all stars, C all stars but one, right? C all stars but two, C all stars but three, and so on. Right. And yeah, so that's one way to think about it. So so whatever is in the first hole will either be a star or a C with, you know, all stars but right. And the second hole will also be either a star or a C with a C all stars but, and so on and so forth. Right. So that's what's going to be in this structure here. Right. And so you want to be able to, since each of these are all the same, you kind of want to have some additional tagging mechanism. So I can use the structure I've already got to label or tag these positions. So now I can know, not contextually, but independent of context, right? Objective or free of context. Whether I'm looking at a zero morphism or a one morphism or a two morphism or an n morphism, etc. Right. And what's interesting is that in that context, all of the dynamical systems operators have meanings, right? So I can do a shift. And in fact, you know, one of the things that I hadn't thought about was, you know, to pull them out entirely. So I can pull this guy out into the plus, right? And so here's an alternate shift operator. Right. So I moved it. I didn't lose information. Right. So this one is information loss in some sense. This one is somehow information preserving. Right. So the infinite part is the infinite gadget is over here, but I've moved all of these into the base case in some sense.
Okay.
Right. So, but the interesting thing is that all of the dynamical systems operators, like shift, are now available to us at the type level. Right. They're giving us an ability to manipulate the type and investigate the structure of the type. So remember, the type is what's giving us the infinity category inhabitants. And now we can look at the dynamics of these possible infinity categories using the dynamical systems operators, right? So that's one of the advantages, let's say, because we have a lot of data. We have a whole machinery that has been built up for you know, the theory of dynamical systems. We know a lot about it, right? And so we can apply all of that machinery to these infinity categories. And we can do that because we've related the two in terms of the type theoretic construction. So that's the one of the advantages of taking an approach like this. So anyway, I just
Mhm.
I just wanted to point out that the recipe that I developed with the reflective operators applies everywhere to every single piece of mathematics, right? So we showed how it applies to process calculi. We showed how it applies to set theory. And here we're beginning to show some of its applications to category theory, right? Where we're beginning to investigate category theory in terms of these reflective operators. And also, I just want to recall the reflective operators can be seen in the light of the derivative, right? So I don't have to, I can think of, I can define a, so if I think of this as a, oops, if I think of this as a infinite variable function, right, then I can think of, uh, so I can do delta zero. Now I'll just leave it as delta, delta RC. And notice what happens. I can relate this to the shift operator. Oops, I grabbed one too many. And then I want to grab this one. Right, you see what I did? I only closed up one of the holes. So this hole has been closed, but these are now still open. Does that make sense?
I'm not following how the derivative is.
So the derivative of C applied to X1 through, right, notice we've dropped X0,
Mhm.
right, is going to be C of the derivative, right? So I closed up the zeroth hole,
Mhm.
right? C has an X0, right? So I close up the X0 hole and I leave X1 through Xn open,
Okay.
right? So it's very similar to what happens with derivative of a function, right? So
Mhm.
imagine that we only had n of these, right? I'm essentially getting rid of the first hole,
Okay.
right? And
Mm.
notice how, so let's call this shift prime. So and notice that there's a connection between shifting, right, and derivatives. The connection is that when I shift, I've also gotten rid of the dynamics that's going on in one of the holes. You see the connection, right? Here, I close up one of the holes reflectively. Here, I drop the information or I move the information over into uh, the the branching part,
Okay.
right? So there's an interesting connection between the derivative and the shift operator, right? Um, and in fact, in general, if you so we can look at what's this? All right, so let me just reorder some of this stuff. put this up here and put this down here. Okay, there we go. And expand this out. There we go. So I can, if I do this, and I do in here, let me just superscript this. All right, so that is going to close it up. So I'm just going to put without having to write all this stuff, because it's going to get really noisy quickly. Okay, understand what has to happen, right? So then this one will be and that will be two. Oops. And all the way out to and this will be n minus 1. Right? So it'll close it up out to here, which means then that if I did here, let me, I think I've got it in my favorites. Oh no, I don't. Let me look for omega. Oops. Here we go. There we go. There we go. Get rid of that. There. I'll get rid of this noise because it's really noise. You see, if we do the omega derivative, that's this RC here.
Okay.
Right. Yeah. There's a little bit of stuff I have to clean up around the +1, the 1 plus, but that's the so that's another way to relate the derivative back to closing up the holes all at once, simultaneously closing up the holes. So I guess the point is that we now have all of this apparatus from well understood machinery, whether we're talking about derivatives or we're talking about shifting. These are all things that are available to us to explore infinity categories using when we adopt the reflective approach. Okay. So we're 2 minutes over. I'll just summarize. The reflective approach is a recipe. It's a principle. Find your dependencies, close them up, right? And we can apply that to process calculi. We can apply that to set theory. We can apply that to graphs, and we can apply that to category theory. So the principle is affects all of mathematics. And that's what I wanted to say for today. Thanks so much.
Very good. Thank you, Greg. We
Yeah,
appreciate
thank
it.
you, Greg.
Yeah, sure.